Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here today because we are embarking on what I like to call a tech history detective story. If you've ever sat back and wondered how on earth we got from the really basic, simple neural networks of the past to the incredibly articulate, massive large language models we use today, well, you are looking at the missing link. Today's deep dive is all about the sequence-to-sequence architecture, or Seq2Seq for short. We're going to explore why this brilliant breakthrough was actually a beautiful failure and how understanding its exact breaking point is, frankly, the absolute best way to truly grasp modern AI. Okay, let's dive right into this with a really fundamental problem. Say you're building an AI to translate English to French. How do you handle the simple fact that sentences don't map one-to-one? I mean, hello is one word and bonjour is one word, sure, but I am hungry translates to j'ai faim, which structurally is totally different. The lengths of these sequences are completely mismatched. So how does the computer deal with that? To really appreciate how hard this was, we got to look at what AI was mostly doing before this. Classification, honestly, is relatively easy. You take a variable length sequence, like, say, an entire movie review, and you just boil it down to a single label, positive or negative. But translation? Translation is chaotic. You're mapping a variable length sequence in one vocabulary to an entirely new variable length sequence in another vocabulary. And there is absolutely zero guarantee of matching lengths. For a long time, standard neural networks just didn't know how to handle this natively. Enter the 2014 breakthrough by researchers Seq2Seq, Vinyals, and Lee. Their recipe was shockingly simple. Instead of inventing some radically complex new math, they took two existing tools, recurrent neural networks, or RNNs, and they just glued them together in a totally novel way. They essentially built a system with two distinct workers, just sort of pretending to be a single translator. Let's meet the first worker in our two-translator analogy, the encoder. Now, the encoder's sole job is to read the source sentence word by word. As it processes the text, it updates its own internal state. The theoretical promise here was that by the time it reaches the very end of the sentence, it has consumed everything and, supposedly, lost absolutely nothing. Now, the truly interesting result of the encoder's hard work is what's called the context vector. You can think of this as the ultimate summary. It's a fixed-size representation of the entire input sentence. If you picture translation as a relay race, this context vector is the vital baton being passed from the first worker to the second. And waiting to receive that baton is our second worker, the decoder. The decoder is really just another RNN, but here's the trick. It's initialized using that exact context vector. It takes that rich summary, predicts the very first translated word, and then, in this brilliant little loop, feeds its own prediction back into itself to guess the next word. It just repeats this cycle over and over until it spits out a special end-of-sequence token, or it hits a hard maximum length limit. If you were actually sitting down and coding this in PyTorch, it condenses into 4 pretty digestible steps. First, you build your encoder, making sure to keep only that final hidden state. Next, you build the decoder so it outputs the probabilities, or logits, of your target vocabulary. Then you set up a training loop to measure exactly how wrong the model's guesses are using cross-entropy loss, which is basically just a mathematical way of scoring its mistakes. And finally, you create an inference loop for when the model actually runs in the wild. But hold on, because those last 2 steps, they introduce a massive complication. Yeah, we need to talk about the messy reality of training this beast. Because, think about it, if you just let a completely untrained decoder guess the next word, and then feed that terrible guess back into itself to make the next guess, well, early mistakes compound quickly. It becomes this awful cascade of errors. The model gets so incredibly confused by its own bad predictions that it practically learns nothing at all. To fix this cascading failure, researchers use a really clever trick called teacher forcing. During training, we don't actually let the decoder eat its own flawed predictions. Instead, the teacher steps in. At every single step, we hand the decoder the actual correct ground truth word from the previous step. It's exactly like having a tutor gently correct you mid-sentence so you can actually succeed in learning the rest of the grammar. This beautifully stabilizes the whole learning process. But there is a massive catch when it comes to inference time, when the model is actually deployed. There's no teacher anymore. The model is suddenly forced to rely entirely on its own previous predictions. This creates a huge gap between how it trained and how it operates out in the real world, and we call that exposure bias. Because the model was always spoon-fed the correct answers during training, it never actually practiced recovering from its own minor mistakes. So engineers had to come up with clever mitigations to bridge this gap. There's scheduled sampling, which slowly dials back the teacher forcing over time, essentially weaning the model off its training wheels. There's minimum risk training, which directly optimizes the model for its actual translation grade. And this brilliantly illustrates a core truth of AI development. Look at that last point, reinforcement learning fine-tuning. Those are the exact same tricks being used to align the massive LLMs via RLHF today. The DNA of 2014 is very much alive right now. Now, how does the model actually pick its words during inference? Well, the simplest way is greedy decoding, just grabbing the highest probability word at every single step. But greedy decoding is dangerous. Once it commits to a bad word, it cannot unsay it. It wanders way off track. That's exactly why we use beam search. Instead of keeping just one guess, beam search keeps the top 3 to 5 partial sequences alive simultaneously, exploring different branching paths before picking the overall best translation at the very end. So, look at what we've got. We have this brilliantly designed machine. 2 RNNs, context vectors, teacher forcing, beam search. It sounds super robust, right? But I want you to pause for a second and really think. What happens if you give this carefully tuned machine a long, say, 40-token input sentence? It crashes right into a brick wall. The brutal reality of this architecture is this. Everything the encoder learned about the source must be squeezed into that one single context vector. I want you to picture this visually. It's literally like trying to pack an entire 40-volume encyclopedia into a single fixed-size carry-on bag. It absolutely does not matter how clever your packing strategy is. Something has to get crushed, lost, or left behind. This fatal flaw is known as the context bottleneck, and here is exactly how the system chokes. Because a single hidden state simply cannot losslessly memorize a long input, long sentences lose crucial detail. Rare words, they get blurred completely out of existence. And complex structural reordering, like flipping the French chat noir to the English black cat, can't be dynamically computed. The model basically just has to brute force memorize it. The baton pass between our two translators simply drops way too much information. And yet, this failure is absolutely spectacular. In fact, it is arguably the most pedagogically useful failure in all of natural language processing. Understanding this exact choke point, the strict inability to pack sequence data into a single, fixed-sized vector, is exactly why modern AI had to evolve. You really cannot understand the modern AI boom without understanding this specific, beautiful failure. So the crucial point here is capturing how all these pieces fit together. If you take a mental snapshot of anything today, make it this translation of dense jargon into actual working mechanics. The encoder reads the source, but hits a bottleneck making the context vector summary. The decoder actually generates the text. We stabilize its learning with teacher forcing, but that creates exposure bias, since it never practiced fixing its own mistakes, which then requires us to salvage its real-world generation using beam search. The whole shebang is interconnected. Now, while transformers ultimately took over the world, the RNN-based Seq2Seq architecture isn't entirely dead. You'll actually still reach for it today in highly constrained scenarios. Think streaming translations with strictly bounded memory, or running on-device generation where massive memory costs are just totally prohibitive. And of course, for pedagogy, because learning this specific system is the absolute fastest path to understanding what ultimately replaced it. Which leads us to our final and perhaps most important question. If the entire context bottleneck happens because the decoder is only allowed to look at the last hidden state of the encoder, well, what if we broke that rule? What if we let the decoder look at every single state the encoder produced? That simple, profound question plants the seed for the mechanism of attention, which would go on to literally rewrite the entire world of artificial intelligence. I really hope this explainer sheds some light on the beautiful failure that made modern AI possible. Keep learning and stay curious.